Nuclear reactors. A nuclear reactor is a very efficient source of energy. The fission of 1 gram of uranium 235 per day involves energy at a rate of about 1 megawatt, whereas 2.6 tons of coal per day must be burnt in a conventional power plant to produce 1 megawatt. The energy given off in a nuclear becomes heat, which is removed by a liquid or a gas coolant. The hot coolant is then used to boil water, and then resulting steam is fed to a turbine that can power an electric generator, a ship, or a submarine. The energy given off in a reactor becomes heat, which is removed by a liquid or gas coolant. The hot coolant then used to boil water, and the resulting steam is fed to a turbine that can power electric generator, a ship, or a submarine. Each fission of 235 uranium releases an average of 2.5 neutrons, so no more than 1.5 neutrons per fission can be lost for self-sustaining chain reaction to occur. However, natural uranium contains only 0.7% of the fissionable isotope to uranium-235. The most abundant 238 readily captures fast neutrons but usually does not undergo fission as a result. As it happens, 238 uranium-238 only has a small cross-section for the capture of slow neutrons, whereas the cross-section of uranium-235 for slow neutron-induced fission is a whopping 582 barns. Slowing down the fast neutrons that are liberated in fission thus helps prevent their unproductive absorption by 238 uranium-238 and at the same time promotes further fission in uranium-235. To slow down fission neutrons, the uranium in a reactor is mixed with a moderator, a substance whose nuclei absorb energy from the last neutrons in collision without much tendency to capture the neutrons. While the exact amount of energy lost by a moving body that collides elastically with another depends on the details of the interaction, in general the energy transfer is a maximum when the participants of equal mass. The greater the difference between the masses, the greater the number of collisions needed to slow the neutron down, the longer the period in which it is in danger of being captured by uranium-238 nucleus. Majority of today's commercial reactors use light water both as moderator and coolant. Each molecule of water contains two hydrogen atoms whose proton nuclei have masses identical to that of neutron, so light water is an efficient moderator. Unfortunately, protons tend to capture neutrons to form neutrons in the reaction. Light water reactors therefore cannot use natural uranium for fuel but need enriched uranium whose uranium-235 content has been increased to about 3%. Unfortunately, protons tend to capture neutrons to form deuterons in the reaction. Light water reactors therefore cannot use natural uranium for fuel but need enriched uranium whose uranium-235 content has been increased to about 3%. Enriched uranium can be produced in several ways. Originally, all enriched uranium was produced by gaseous diffusion, with uranium hexafluoride gas being passed through about 2000 successive permeable barriers. Molecules of uranium-235 uranium hexafluoride are slightly more likely to diffuse through each barrier than uranium-235 238 hexafluoride because of their small mass. A more recent method with high-speed gas centrifuges for the separation. Still other processes are possible. Enriched uranium can be produced in several ways. Originally, all enriched uranium was produced by gaseous diffusion, with uranium hexafluoride gas being passed through about 2000 successive permeable barriers. Molecules of uranium 235 hexafluoride are slightly more likely to diffuse with each barrier than 238 because of their smaller mass. A more recent method uses high gas centrifuge for their separation. Still, other processes are possible. The fuel for water-based, water-moderated reactor consists of uranium oxide pellets sealed in long thin tubes, control rods of cadmium or boron which are good absorbers of slow neutrons can be slid in and out of the reactor core to adjust the rate of nuclear chain reaction. In most common type of reactor, the water that circulates around the fuel in the core is kept at high pressure of about 155 atmospheres to prevent boiling. The water, which acts as both moderator and coolant, is passed through the heat exchanger to produce steam that drives the turbine. Such a reactor might contain 90 tons of uranium oxide and operate at 3400 megawatt to yield 1100 megawatt of electric power. The reactor fuel must be replaced every few years as its uranium 238 content is used up. Control rods of cadmium or boron, which are good absorbers of slow neutrons, can be slid in and out of the nuclear reactor core to adjust the rate of chain reaction. In the most common type of reactor, water that circulates around the fuel in the core is kept at high pressure. The fuel for a water moderated reactor consists of uranium oxide pellets sealed in long, thin tubes. Fuel rods are being loaded in the core of 1100 megawatt reactor in this nuclear power plant. Breeder reactors, some non-fissionable nuclides can be transmuted into fissionable ones by absorbing neutrons. A notable example is uranium 238. Non-fusionable nuclide, it can be transmuted into fissionable one by absorbing neutrons. Uranium 235 uranium 238, which becomes uranium 235 when it captures a fast neutron. The This uranium isotope beta decays with a half-life of 24 minutes into neptunium, an isotope of elemental neptunium which is beta active. The decay of neptunium 239 has half-life of 2.3 days and yields plutonium, an isotope of plutonium. His half-life is against alpha decay is 24,000 years. The entire sequence is shown in figure 12.24. Both neptunium and plutonium are transuranic elements, none of which are found on the Earth because their half-lives are too short for them to have survived even if they had been present when the Earth came into being 4.5 billion years ago. The plutonium isotope is fissionable and can be used as a reactor fuel for weapons. The plutonium isotope is fissionable and can be used as a reactor fuel for weapons. Plutonium is chemically different from uranium, and its separation from the remaining uranium 238 after neutron irradiation is most easily accomplished than the separation of uranium 235 from the much more abundant uranium 238 in natural uranium. A breeder reactor is specially designed to produce more plutonium than the uranium 235 it consumes because the otherwise unless uranium 238 is 140 times more abundant than the fissionable 235. The widespread use of breeder reactors would mean the known reserves of uranium could fuel reactors for many centuries to come because plutonium could also be used in nuclear weapons, unlike the slightly enriched uranium that fuels ordinary reactors. The widespread use of breeder reactors would also complicate the control of nuclear weapons. Several breeder reactors are operating today all of them outside the United States. They have proved to be extremely expensive and have several operating problems. Actually, plutonium is already an important nuclear fuel. By the end of the usual 3-year fuel cycle in a reactor, after which the fuel rods are replaced, so much plutonium has been produced from the uranium 238 present that more fissions occur in the plutonium than in uranium 235. So figure 12.24, uranium 238 and thorium 232 are fertile nuclides. Each becomes fissionable nuclides after absorbing a neutron and undergoing two beta decays. So first beta decay, it becomes uranium 239, then against a beta decay it becomes neptunium 239, and then against a beta decay it becomes plutonium. So it becomes thorium first, then these transformations are basis of breeder reactor, which produces more fuel in the form of plutonium or uranium 233 and then uses it up in the form of uranium 235. These transformations are the basis of breeder reactor, which produces more fuel in the form of plutonium 239, then it uses up it in the form of uranium 235. Basic design of the most new type of nuclear power plant. Water under pressure is both moderator and a coolant and transfers heat from the chain reaction in fuel rods of both core to steam generator. The resulting steam then passes out of the containment shell, which serves as a barrier. Water under pressure, water is both moderator and a coolant and transfers heat from the chain reaction in the fuel rods of the core to the steam generator. The resulting steam then passes out of the containment shell, which serves as a barrier to protect the outside world from accidents. In a typical plant, the reactor vessel The resultant steam then passes out of the containment shell, which serves as a barrier to protect the outside world from accidents to the reactor and is directed to a turbine that drives an electric generator. In a typical plant, the reactor vessel is 13.5 meter high and 4.4 meter in diameter and weighs about 385 tons. It contains about 90 tons of uranium oxide in the form of 50,000 fuel rods, each 3.85 meter long and 9.5 meter in diameter, millimeter in diameter. Four steam generators are used instead of a single one shown here, as well as number of turbine generators. In, nine, in 1951, the first electricity from a nuclear plant was generated in Idaho. Today, over 400 nuclear reactors in 26 countries produce 200,000 megawatt of electric power, the equivalent of nearly 10 million barrels of oil per day. France, Belgium, and Taiwan obtain more than half of the electricity from reactors, with several other countries close behind. Today, 400 nuclear reactors in 26 countries produce 200,000 megawatt of electric power, the equivalent of nearly 10 million barrels of oil per day. India is nowhere to be seen here. In the United States, nuclear energy is responsible for 21% of generated electricity, slightly more than the world average. There are 103 reactors in 31 states. Yet, for all the successes of nuclear technology, no new nuclear power stations have been planned in this country since 1979. Why not? In March 1979, failures in its cooling system disabled one of the reactors at the Three Mile Island in Pennsylvania, and a certain amount of radioactive material escaped. Although a nuclear reactor cannot explode in a way an atomic bomb does, breakdowns can occur that put large population at risk. Although a true catastrophe was narrowly avoided, the Three Mile Island incident made it clear that the hazards associated with nuclear energy are real. After 1979, it was inevitable that greater safety would have to be built into new reactors, adding to their already high cost. In addition, demand for electricity in the United States was not increasing as fast as expected, partly because of efforts towards greater efficiency and partly because of decline in some of industries such as steel, cars and chemicals that are heavy users of electricity. As a result of these factors, new reactors made less economic sense than before, which together with widespread public unease led to halt in the expansion of nuclear energy in the United States. Elsewhere, the situation was different. Nuclear reactors still seemed the best way to meet the energy needs of many countries with abundant fossil fuel resources. Then in April 1986, a severe accident destroyed a 1,000 megawatt reactor at Chernobyl, what is now in Ukraine. Then part of the Soviet Union, this was the worst environmental disaster of technological origin in history and contributed to the collapse of Soviet Union. Over 550 tons of radioactive material escaped and was carried around the world by winds. The radiation released was nearly 200 times the total gas given off by Hiroshima and Nagasaki atomic bombs in 1985. Radiation levels in much of Europe rose well above the normal for a time, and a quarter of a million people were permanently evacuated from a vicinity of Chernobyl. A number of reactor rescued a number of reactor rescue and cleanup workers died soon after as a result of exposure to radiation, and thousands more became ill. Widespread contamination with radionuclides, particularly of food and water supply, suggests that cancer will raise the total of people affected manyfold in the years to come. Already about 1,000 children who are especially susceptible have developed thyroid cancer as a result of ingesting radioactive iodine isotope. A third of children living near the Chernobyl who were under 4 years old in 1986 are expected to come down with a thyroid cancer eventually. As in the United States after Three Mile Island, public anxiety over the safety of nuclear programs grew in Europe after Chernobyl. Some countries, for instance Italy, abandoned plans for nuclear reactors. In other countries, for instance France, the logic behind their nuclear programs remained strong enough for them to continue despite Chernobyl. Quite apart from the safety of reactors themselves is the issue of what to do with the waste they produce. Even if the old fuel rods are processed to separate out the uranium and plutonium they contain, what is left is still highly radioactive. Although a lot of activity will be gone in a few months and much of the rest in few hundred years, some of the radionucleotides have half-lives in the millions of years. At present, perhaps 20,000 tons of spent nuclear fuel is being stored on a temporary basis in the United States, not to mention the vast amount of radioactive waste left over from nuclear weapons manufacture that is also awaiting safe storage. Burying nuclear waste deep underground currently seems to be the best long way to dispose them. Right location is easy to specify but not easy to find. Stable geologically with no earthquakes, likely no nearby population centers, a type of rock that does not disintegrate in the presence of heat and radiation but is easy to drill into, and not near groundwater that might become contaminated. From today's perspective, nuclear energy has an important advantages but not fully appreciated in the past. It does not produce air pollution that fossil fuel burning does, nor the huge quantities of carbon dioxide that are the main contributor to global warming via the greenhouse gas effect. Today, with the rising cost of fossil fuels and increasing demand for electricity, these factors seem likely to lead to the construction of new nuclear reactors in the United States after the delay of over 2 decades. So that's all. See you in the next one.